The alternating harmonic series, the sum from 1 to infinity of -1 to n minus 1 divided by n, which is basically 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6. Let's write a few terms, plus 1/7 and so on. Okay, this is a conditionally convergent series. That means that it converges, okay, but it does not converge absolutely. Okay, because if we take the absolute values of the terms in the series, we get the harmonic series, which we know it's not convergent. And actually, just a side note, turns out, let's call it S for the sum of the alternating harmonic series. I was saying, turns out the sum is equal to the natural logarithm of 2. And this is actually easy to do. Just do the Taylor expansion of the function logarithm of 1 plus x and evaluate at x equals 1. You will get this precise alternating harmonic series. Okay, so this is one resource that we can use. But now, this alternating harmonic series has a very striking feature. Let me show you one proof that we can do using this series. So again, let's write it in expanded form. Okay, let me copy these few terms. Actually, I think we are going to need a few more if we are going to see what I want to show. So let's write a few more: -1/8, plus 1/9, -1/10, plus 1/11. Let's write one more. -1/12, and so on. Okay. Now, let's multiply this series by 2. So what do we get? We get 2 minus 1 plus 2/3 minus 2/4, but that's 1/2, plus 2/5 minus 1/3, plus 2/7 minus 1/4, plus 2/9, minus 1/5, plus 2 divided by 11, minus 1/6, and so on. It keeps going. Okay, and now let's simplify things here, because actually if we look carefully, so we have two integers here, then we have numbers with denominator 3. We also have some that have denominator 2, right? Actually only one. But with 5 we have 2 at least, okay? And so on. Actually only 2. And what we can do, we can rewrite just collecting terms with the same denominator. So let me write that down. Rewrite collecting terms with the same denominator. Okay. So what we get is 1 plus, well, actually, let me rearrange. So this is minus 1/2, this 1/2 here. Then let's use blue, plus 1/3. Then the negative 1/4 is over here, minus 1/4. Then we have the 5th, 2/5 minus 1/5, which is plus 1/5. and then we have minus 1 over 6. Okay, and we can keep going. So the next one will be plus 1 over 7, and so on. That one comes from the 2/7 from here, and then we have a negative 2 over 14 that will appear later on down the road. Okay, but what I want to remark is that actually what did we get here? 1 minus 1 half plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/7, and so on, which is the original series that we know that is non-zero. So what happened here? 2 equals 1. Is that what we have proved? So obviously there is something wrong in this argument. We have done something that we shouldn't or that we couldn't. And this is something that was pointed out by Dirichlet. Okay, in the 19th century, 1827, he pointed out this example and he said, well, something is happening here. He was investigating the convergence of Fourier series, okay, that is related to waves, okay? And he couldn't really give a reason why this happened. We are going to investigate why this happened. What he was able to show is that if the series is absolutely convergent, okay, we can rearrange the terms in whichever way we want. The sum will not change. So it can be rearranged without changing the sum. Obviously, here I already told you what's the problem in the argument, okay? The problem is multiplying by 2 is okay, no problem. The problem is that we have rearranged the terms of the series. Did you notice? So instead of computing the series in order, okay, the terms appear in a very precise order, I decided to change them. Okay, but when I do that, I'm changing the result because some of them are positive, some of them are negative. Okay, and when that happens, it may happen like in here that you can change the trend, okay, like adding more positive terms together or more negative terms together. And actually, our main goal here is to prove a result by Riemann. Okay, this was circa 1872 or 73, although it was published later. So he was able to show that whenever we have a conditionally convergent series, okay, such as the alternating harmonic series, whatever number we choose, we will be able to find a rearrangement of the series that converges to that number. So you pick a number, know for sure there is any number. There is a rearrangement of the series that converges to that number. So that is our goal, to prove that result. In fact, let's continue with the same example, the alternating harmonic series. Okay, 1 minus 1 half, well, actually, there we go. And let's consider some specific rearrangement different from the one we already did. Okay, in this case, what I'm going to do, I'm going to do first the 1/3, okay, then take out 1/2, then add 1/5, then add 1/7. Then I'm going to take out 1/4. And then I'm going to add 1/9 and 1/11. Then I'm going to subtract 1/6, and so on. You have probably figured out the pattern here. What I'm doing is, and I'm adding together two positive terms, and then subtracting one negative. Two positive, then one negative, and so on. Here, notice that what happens to the series is that it builds up twice, then goes down a little. Up twice, then down a little. So here we are always going to be subtracting less than we added, okay? So, but actually much less. So let's estimate. What we are going to do is we are going to estimate the two sums to see that they give different results. So let's again call S the sum of the first series. Okay, and let's estimate. Well, we already know it's logarithm of 2. Okay, so that one we don't have to estimate, but if we didn't know, one way we could estimate is realizing, okay, if I take the sum S is going to be smaller than the sum of the first three terms. Why? Because then the next one is subtracting negative 1/4. But then I add 1/5. That is not enough to recover that negative 1/4. And then I subtract again, and then I add a little, but I'm always, the trend is to subtract. Okay, and this is 5/6. Again, this is this idea of the estimate. We don't need to do it because we already know, I shown you that the sum is logarithm of 2. But you can use this idea in situations where you don't know the particular, the precise sum. Okay, so we have an estimate that says that the sum is less than 5/6. And now what we are going to show is that actually the rearrangement that we can call S prime is actually bigger than 5/6. Okay, and if we do that, we know for sure that the two series, the series and the rearrangement, will have a different sum. So for the rearrangement, we are going to look at blocks of three terms. Okay, positive, positive, negative, positive, positive, negative, and so on. Okay, and if we look at these terms, we can figure out a formula for these blocks. Okay, so it will be 1/4k minus 3 plus 1/4k minus 1 minus 1/2k. Okay, this is the general way to write them, for k bigger or equal than 1. You can check. Now, the thing that is important for us is that actually when we look at these blocks, they are always positive. Okay, so what happens then? If these blocks are all positive, then if I look at the partial sums and I look at S3, which is the sum up to that negative 1/2, okay, this one is going to be smaller than S6, okay, which is the first two blocks, okay, plus 1/5, plus 1/7, minus 1/4, and so on, okay. And in general, I'm going to get S3 less than S6, less than S9, and so on, okay. So what happens here? what happens here is that the lim sup as n tends to infinity of these partial sums, it's going to be bigger, right? Because it has a, you notice here, we have chosen a sequence that is increasing. So the lim sup, if we follow this sequence, is going to be at least as big as the first one, the first term, okay, which was 1 plus 1/3 minus 1/2, okay, and that turns out to be 5/6, okay, because notice that it's precisely the same three terms that we had in our estimate, only they have been rearranged. Now here, something that is very important is that when we have a finite sum, it doesn't really matter how we add the terms together. It will always be the same. But when we have an infinite number of terms in the sum, then the order may be very important.